You know, people ask me all the time, what is time? And I have to tell them right off the bat, you're asking the wrong question. You're asking what is time as if time is a thing, like a rock or a piece of cheese, something you could hold in your hand and examine. But time isn't a thing at all. Time is a way we've invented to keep track of change. And once you understand that, once you really get that deep in your bones, the whole mystery starts to look different. Now let me tell you something interesting. When I was a kid, I had a clock in my room, one of those wind-up kinds with the little tick-tock sound, and I used to lie there at night listening to it. Tick-tock, tick-tock. Regular as anything. And I thought, well, that's time passing. Each tick is a moment of time going by. But here's the thing. The clock isn't measuring time. The clock is just a machine with gears that move in a regular way, and we've agreed to call that movement time. We could just as easily have used the dripping of water, or the burning of a candle, or the swing of a pendulum. They're all just physical processes that happen at roughly constant rates, and we've picked one and said, okay, we'll use this to measure all the other changes happening around us. So what is actually happening when we say time is passing? Well, things are changing, that's it. Atoms are moving. Particles are interacting, electrons are jumping between energy states, photons are traveling through space. All these physical processes are occurring, and we've invented this concept called time to organize our descriptions of these changes. It's a bookkeeping device, a very useful one, don't get me wrong, but it's not some fundamental substance flowing through the universe like a river. Now here's where it gets really interesting. In physics, when we write down the equations that describe how the universe works, time appears as a parameter. It's a variable, just like the position of a particle or its momentum. In classical mechanics, Newton's equations, you have time showing up as t, and you can calculate where something will be at any value of t. You can even, mathematically speaking, run time backwards. If you film a bunch of billiard balls bouncing around on a table and then play the film in reverse, the reverse motion still obeys Newton's laws perfectly. The equations don't care which direction time is going. But wait, you say, that can't be right. We all know time only goes forward. We get older, not younger. Eggs break, but they don't unbreak. Coffee cools down, but it doesn't spontaneously heat back up. There's definitely an arrow to time, a direction. And you're absolutely right. There is an arrow, but it doesn't come from the fundamental laws of physics. It comes from something else entirely, something called entropy. Let me explain entropy the way I like to think about it. Imagine you have a box, and in one corner of this box, you've put all the air molecules. All of them, every single one, crammed into just one tiny corner. Now, you open a little door in that corner, and what happens? The molecules spread out. They fill the whole box. They don't stay in the corner. Why not? Because there are vastly more ways for the molecules to be spread throughout the box than there are for them all to be in one corner. If you think about it statistically, which is what we do in thermodynamics, any particular arrangement where molecules are spread out is just one of trillions upon trillions of possible arrangements. But there are very few arrangements where all the molecules happen to be in one corner. So entropy is really just a measure of how many ways you can arrange the components of a system while still having it look the same macroscopically. A high entropy state is one where there are lots and lots of possible microscopic arrangements. A low entropy state is one where there are very few. And here's the key. Systems naturally evolve from low entropy states to high entropy states, not because there's a law forcing them to, but simply because there are more high entropy states to be in. It's a statistical thing, a matter of probability. And this is where the arrow of time comes from. The universe, for reasons we don't fully understand, started out in a very low entropy state, very organized, very special. And ever since then, it's been evolving toward higher entropy states. That's why eggs break and don't unbreak. That's why we age. That's why coffee cools down. All these processes are manifestations of entropy increasing, of the universe exploring more and more of the available states, spreading out in configuration space if you want to get technical about it. But here's something that'll really bake your noodle. The fundamental laws of physics, quantum mechanics, electromagnetism, even general relativity, they're all time-symmetric. They work just as well going forward as going backward. If you take any allowed physical process and run it in reverse, you get another allowed physical process. So the arrow of time, this feeling we have that time only goes one way, it's not in the fundamental laws, it's in the initial conditions. It's in the fact that the universe started out in this very special, very low entropy state, and it's been running downhill, entropically speaking, ever since. Now let's talk about Einstein and relativity, because this is where things get really wild. Before Einstein, everybody thought time was absolute. There was one universal clock ticking away, the same for everyone everywhere. If something happened at a certain time for you, it happened at that same time for me, for someone on Mars, for someone in another galaxy. Time was just this universal background against which events occurred. But Einstein showed that's completely wrong. Time is relative. It depends on how you're moving. If you're moving relative to me, your clock runs at a different rate than mine. This isn't some illusion or trick. It's not that your clock is broken. It's that time itself is passing at a different rate for you than for me. And this has been tested over and over again. We put atomic clocks on airplanes and fly them around, and when we bring them back, they've measured a different amount of time than identical clocks that stayed on the ground. The difference is tiny because airplanes don't go very fast compared to the speed of light, but it's there. And it's exactly what Einstein predicted. And it gets stranger. Not only does time run at different rates depending on how you're moving, but events that are simultaneous for one observer aren't simultaneous for another. Imagine you're on a train and you're right in the middle of the train car. You set off 2 firecrackers, one at the front of the car and one at the back, and you arrange it so the light from both explosions reaches you at the same instant. For you, those 2 explosions happened at the same time, simultaneously. But for someone standing on the platform, watching the train go by, the explosion at the back happened first, because the train was moving toward the light from the back explosion and away from the light from the front explosion. For them, the events aren't simultaneous. So, simultaneity, this notion that 2 things happen at the same time, it's not absolute. It depends on your frame of reference, on your state of motion. And if simultaneity isn't absolute, then the whole idea of now, of the present moment, it's not absolute either. My now is different from your now if we're moving relative to each other. This leads to something really profound. In relativity, we don't think of space and time as separate things. We think of them as unified into something called spacetime. It's a 4-dimensional structure, 3 dimensions of space and 1 of time, all woven together. Events don't happen in space at a certain time. Events just happen at particular locations in spacetime, particular points in this 4-dimensional continuum. And here's the kicker. From the perspective of spacetime, of this 4-dimensional view, the past and the future are just as real as the present. They're all just different regions of space-time. When we say time is passing, what we really mean is that our consciousness, our experience, is moving through space-time, encountering different events in sequence. But those events don't pop into existence when we encounter them and then disappear after we've passed them. They're all just there, laid out in space-time. This is called the block universe view, and it's a natural way to think about relativity. The entire history of the universe, from the Big Bang to the far future, it's all just there, existing as a 4-dimensional structure. Past, present, and future are all equally real. They're just different locations in space-time, like north, south, east, and west are different locations in space. Now, I know what you're thinking. If the future already exists out there in space-time, doesn't that mean everything is predetermined? Doesn't that mean we don't have free will? And I have to tell you, that's a much harder question. And it's not really a physics question. It's a philosophy question. Physics can tell you how things evolve according to the laws of nature, but it doesn't really address this feeling we have of making choices, of our actions being up to us. But let me point something out. Even in classical physics, even before relativity and quantum mechanics, there was already a tension with free will. If the universe is just particles moving according to Newton's laws, and if you specify the positions and velocities of all the particles at one moment, then in principle you can calculate where they'll all be at any future moment. Everything is determined by the initial conditions and the laws of physics, so the free will question was already there. Relativity just makes it more vivid by suggesting that the future is already laid out. Quantum mechanics throws another wrench into all this, because in quantum mechanics the future isn't determined, not even in principle. If I have an electron in some state and I measure its position, I can't predict exactly where I'll find it. I can only calculate the probability of finding it in various locations. The outcome is genuinely random, not just unknown, but unknowable in advance. So quantum mechanics gives you a kind of indeterminism, a kind of openness to the future that isn't there in classical physics. But even with quantum mechanics, we still use time as a parameter in our equations. We have this thing called the Schrödinger equation that tells you how the quantum state of a system evolves over time. Time is still there, still playing the role of organizing change, of parameterizing the evolution of the system. Now here's something really deep. When you try to combine quantum mechanics with general relativity, which is our best theory of gravity and space-time, you run into problems. And one of the problems is this. In general relativity, space-time is dynamic. It's not a fixed background. The The shape of spacetime, the geometry of spacetime, depends on where matter and energy are, and it changes as matter and energy move around. Spacetime is part of the physical system, not just a stage on which physics happens. But in quantum mechanics, we're used to having time as this external parameter, this background variable that isn't part of the quantum system itself. So when you try to do quantum gravity, to quantize space-time itself, you have to figure out what to do about time, and this is where things get really weird. In some approaches to quantum gravity, time disappears entirely at the fundamental level. There's no time variable in the basic equations. Instead, the fundamental description is timeless. It's just a specification of relationships between different parts of the quantum state, with no reference to anything changing or evolving. Now, if that's true, if the fundamental theory is timeless, then where does time come from in our experience? Well, it emerges. Just like temperature emerges when you have a bunch of molecules bouncing around, even though individual molecules don't have a temperature. Just like solidity emerges when you have atoms arranged in a crystalline structure, even though individual atoms aren't solid. Time might emerge from some more fundamental, timeless description when you look at the system in the right way, when you coarse grain, when you zoom out and look at macroscopic variables rather than the exact quantum state. This is still very speculative, very much at the cutting edge of research in quantum gravity, and I don't think anyone really knows the answer yet. But it's a fascinating possibility. It suggests that time, this thing that seems so fundamental to our experience, so basic to how we think about the world, might not be fundamental at all. It might be an emergent phenomenon, something that appears only at a certain level of description, like the way waves appear on the surface of water, even though the individual water molecules are just jiggling around. Let me try to tie this together. What is actually happening when we experience time passing? Well, on the one hand, things are changing. Physical systems are evolving from one state to another. Particles are interacting. Fields are fluctuating. Entropy is increasing. That's the objective physical process. On the other hand, we have this subjective experience of time, this feeling of moments passing, of the present moment continuously moving forward. And that subjective experience, that's a product of how our brains work, of how our consciousness is structured. Our brains are physical systems, made of neurons and synapses, and they operate by storing information about the past and making predictions about the future. Memory is a physical process. It involves changes in the connections between neurons, and those changes have a direction. We remember the past, not the future, because our brains are structured by past events. Signals have propagated from those events to our brains, leaving traces, creating memory. So our experience of time, our feeling that there's a now that's moving forward, that's intimately connected to how our brains process information, how they're structured by past events and oriented toward future predictions. It's a cognitive phenomenon as much as a physical one. And interestingly, different parts of our brain seem to have different time scales. Some processes happen very fast, milliseconds, and some happen slowly, over seconds or minutes. So even the unity of the present moment, the feeling that there's one single now, that's a construction, a way our brain integrates information from different processes operating at different rates. Let me give you an example of how weird our perception of time can be. You've probably experienced this. You're doing something really engaging, really absorbing, maybe playing a game or having an intense conversation, and suddenly you realize hours have passed. Where did the time go? It felt like minutes, or the opposite. You're bored, waiting for something, and every minute feels like an eternity. Time drags. But your watch, if you look at it, it's ticking away at exactly the same rate. So your subjective experience of duration, how long something feels, it's not directly tied to the physical process we call time. It's tied to what your brain is doing, how it's processing information. There are also these strange things that happen at very short time scales. If you see two flashes of light very close together in time, less than about a 20th of a second apart, you can't tell which one came first. Your temporal resolution isn't good enough. So, at very short time scales, your perception of order, of sequence, it breaks down. And there's this weird phenomenon called the flash lag effect. If you have a moving object and you flash a light right next to it, the light appears to lag behind the object even though they're actually in the same place at the same time. Your brain processes the moving object differently than the flash, and it creates this illusion of temporal lag. So our perception of time is full of these quirks and illusions. It's not a direct readout of some fundamental time parameter in the universe. It's a construct, a model that our brain builds to make sense of the world, to organize our experiences and memories and predictions. Now, does all this mean time is an illusion, that it's not real? Well, it depends on what you mean by real. If you mean, is there some fundamental substance called time flowing through the universe, some cosmic river carrying us from past to future, then no, that's not real. There's no such thing. But if you mean, do things change? Do physical processes evolve from one state to another? Do we experience a sequence of events? Then yes, absolutely, that's real. That's as real as anything. Time is real in the same way that temperature is real. Temperature isn't a fundamental property of individual atoms. Atoms don't have temperature. But when you have a lot of atoms together, moving around with various speeds, you can define this thing called temperature, which is related to the average kinetic energy, and it's a very useful concept. It describes something real about the system, even though it's not fundamental, and it's the same with time. Time isn't fundamental, not in the way we usually think about it, but it's a very useful way to organize our description of change, and the changes themselves are absolutely real. Here's another way to think about it. Imagine you're watching a movie. The movie is recorded on a piece of film, and every frame is just sitting there on the film. The whole movie exists all at once as a physical object, but when you watch the movie, you experience it as unfolding in time. You see one frame, then the next, and you perceive a story with a beginning and middle and end. The movie itself doesn't change. It's just sitting there. But your experience of the movie unfolds in time. Maybe the universe is like that. Maybe all of history is laid out in space-time, like frames on a film, and our experience of time is like watching the movie. We encounter events in sequence. We have memories of past frames and anticipations of future frames, and that creates this feeling of time passing. But the events themselves, they're just there, existing in space-time. I don't know if that's exactly right. Nobody knows for sure. But it's consistent with what we know from relativity, and it helps make sense of this weird fact that the laws of physics don't have a built-in arrow of time, even though our experience very much does. Let me tell you one more thing that really gets me. In quantum mechanics, we have this thing called entanglement. Two particles can be connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and it bothered him. It seemed to violate the principle that nothing can travel faster than light. But it's real. We've tested it extensively, and entanglement is a genuine feature of quantum mechanics. Now here's the thing. When we describe entanglement mathematically, we don't really use the concept of time very much. We just describe the joint quantum state of the two particles. And this state doesn't refer to any particular moment in time. It's a timeless description of a relationship between the particles. And when you measure one particle, you instantly learn something about the other, but there's no signal traveling from one to the other. There's no cause and effect in the usual sense. It's more like the two measurements are correlated because of this pre-existing quantum relationship. This suggests that at the quantum level, the temporal structure of events, the notion of one thing happening before another, it might not be as fundamental as we think. The relationships between quantum systems might be more basic than the temporal order of events. And this fits with the idea I mentioned earlier that in quantum gravity time might not be fundamental. The basic description might be in terms of quantum correlations and entanglements, with time emerging only when you look at the system in a certain way. So what's actually happening? Change is happening. Systems are evolving, entropy is increasing, particles are interacting, quantum states are collapsing when measurements are made. All of that is real physical process. But the framework we use to describe these processes, the concept of time as a parameter that measures change, that's something we've invented. It's a tool, a way of organizing our description of reality. And at the deepest level, when we try to understand quantum gravity and the nature of space-time itself, time might not appear in the fundamental equations at all. It might emerge only when we step back and look at the world through the limited lens of our macroscopic experience. I find this deeply fascinating and also kind of liberating. It means that time, this thing that seems to constrain us, that seems to be slipping away from us constantly, it's not some external force acting on us. It's a feature of how we describe the world, how we organize our experience. The universe isn't really moving through time like a train moving along a track. The universe just is a four-dimensional or maybe even timeless structure, and our experience of moving through it, that's something that arises from how we're embedded in it, how our consciousness interacts with it. And maybe that can change how we think about our lives. We're not racing against some cosmic clock. We're not running out of some finite substance called time. We're just experiencing change, participating in the unfolding of the universe, which is already laid out in its entirety if the block universe view is right. or which is evolving according to quantum probabilities if you take quantum mechanics seriously. Either way, time isn't something outside us that we're subject to. It's part of how we relate to the world, part of the structure of our experience. So the next time someone asks you what time is, you can tell them this. Time is how we keep track of change. It's a parameter in our equations, a dimension in spacetime, an emergent feature of macroscopic systems with increasing entropy. It's not a fundamental substance. It doesn't flow like a river. It's a way of describing relationships between events, between states of physical systems. And our experience of time, that's a product of how our brains work, how they store information about the past and make predictions about the future. Time is real as a concept, as a tool, as an aspect of our experience. But it's not real as a fundamental feature of the universe at the deepest level. And understanding that, really getting that, it changes everything.